In the last lectures, we were discussing natural convection. Okay. Okay. In a two-dimensional coordinate system, I had expressed the mass, momentum and energy conservation equation for natural convection in 2 dimensions for an object of characteristic dimension LC, okay, where the characteristic length for diffusion is small compared to LC. Okay. Recall that there were 2 dimensionless groups in this problem. One was the Grashof number, which is equal to rho infinity square beta g into T naught minus T infinity LC cubed by mu infinity square, okay, where the surface temperature of the object is T is equal to T naught. The temperature far from the object is T is equal to T infinity. Okay. The temperature far from the object is T equals T infinity. Okay. And beta was the thermal expansion coefficient. Okay. When the Grashof number and the other dimensionless group was the Prandtl number is equal to the kinematic viscosity divided by the thermal diffusivity. Okay. Both of them in the Boussinesq approximation calculated at the temperature of the ambient itself. Okay. We had postulated a thin boundary layer of thickness delta star, small compared to the characteristic dimension of the object in the limit of large Grashof number, because the Grashof number is a square of the Reynolds number based upon the characteristic velocity. When the Grashof number is large, you would expect diffusion to be restricted to a thin region close to the surface, because any momentum or energy that diffuses from the surface will be rapidly swept downstream due to the strong flow. Okay. And if the boundary layer thickness is small, then we can use a local coordinate system, consider the surface to be locally plane surface for analyzing the temperature and the flow in the boundary layer, and use a local approximation where the streamwise direction is x, the cross stream dimension is z. The streamwise coordinate was scaled by the characteristic dimension. Okay. The cross stream coordinate was scaled by the boundary layer thickness. Okay. The streamwise velocity was scaled by the characteristic velocity. Okay. The cross stream velocity was scaled by delta times the characteristic velocity, because from the mass conservation equation, partial Vx by partial x plus partial Vz by partial z has to be equal to 0. Okay. The temperature scaling was T minus T infinity by T naught minus T infinity. Okay. And the dynamical part of the pressure was scaled by rho Vc square. Okay. So, these were the scalings that we had used. And based upon these scalings, the mass, momentum and energy conservation equations that resulted, after neglecting all terms that were order delta or smaller, okay, in the equations, we got partial V by partial x, okay, plus partial Vz plus by partial z plus is equal to 0, mass conservation equation. Okay. Recall that we had got the boundary layer thickness as delta star is equal to Grashof number to the minus 1 by 4. This was the scaling that was required for a balance between convection and diffusion in this boundary layer in the limit as the Grashof number goes to infinity. Okay. The momentum conservation equation in the streamwise direction, okay, the scaled equation. In the cross stream direction, the conservation equation was simply 0 is equal to minus partial p d by partial z. That was what it reduced to. And the energy conservation equation was Vx star partial t by partial x plus Vz plus partial t by partial z plus is equal to 1 by Prandtl number partial square and the boundary conditions are T star is equal to 1 on the surface in scaled coordinates and T star is equal to 0 far away, okay, when expressed in terms of the scale variable. Okay. And you can see that in these equations there are no parameters apart from the Prandtl number. Okay. There is only one parameter in these equations, which is the Prandtl number. The boundary conditions do not have any parameters. At z is equal to 0, T star is 1. As z goes to infinity, T star is equal to 0. So, there are no parameters here. The only parameter in the equations are the Prandtl number. Okay. So, therefore, the solution for the temperature, okay, solution for T star, okay, depends only on the Prandtl number. Okay. Solution for T star in terms of z plus and x star. Okay. So, this solution for T star locally will depend only on the Prandtl number. Okay. There are no other parameters here. Okay. How do we find the heat flux? Okay. Qz is equal to minus k partial T by partial z at z is equal to 0. Substitute in terms of scaled variables k into T naught minus T infinity by Lc, okay, Lc delta star, okay, partial T star by partial z plus at z plus is equal to 0. Okay. And you can see that locally the heat flux depends only upon the boundary layer thickness times partial T star by partial z plus. That derivative can depend only upon the Prandtl number and the geometry. Okay. That derivative can depend only upon the Prandtl number and the geometry. Okay. Now, the average flux is equal to integral over the surface of Qz. Okay. Is equal to minus k into T naught minus T infinity by Lc delta star, okay, 1 over the total area. Okay. I should note the average flux I have to divide by the surface area. Okay. Divide by the surface area, this integral over 1 over the surface area, integral over the surface area of partial T star by partial z plus at z plus is equal to 0. Okay. And the Nusselt number, okay, is going to be equal to Q average by k into T naught minus T infinity by Lc. Okay. So, this is going to be equal to minus 1 over delta star 1 over s integral ds partial T by partial z at z z plus. Okay. This first term, the first term here 1 over delta, okay, is Grashof number to the 1/4. Okay, the first term here 1 over delta is Grashof number to the 1/4 power. Okay. And this second term here, okay, it's going to be negative because dt by dz is negative if there is heat, if the temperature at the surface is higher than the ambient. So, it's going to be negative, and it is only a function of the geometry and the Prandtl number. Okay. So, therefore, this has to be some constant which is geometry dependent, which depends only on the Prandtl number. Okay. So, from the scaling analysis, this is the correlation for the Nusselt number. It is equal to the Grashof number to the 1/4 times some function for the Prandtl number, okay, some unknown function of the Prandtl number, because that Prandtl number appears in the equation. Okay. It is the only parameter that appears in the equation. Okay. There is no parameter in the boundary condition. So, the solution can depend only upon the geometry and the Prandtl number. Okay. In particular, the solution depends upon the orientation of the gravity vector with respect to the surface at different locations and the Prandtl number. Okay. So, this is a constant which depends upon the Prandtl number, and it also depends upon the geometry. So, just from scaling the equations, we get the result that the Nusselt number has to be Grashof number to the 1/4 power, because the boundary layer thickness is proportional to Grashof number to the minus 1/4 power. Okay, and therefore, the Nusselt number has to be proportional to Grashof number to the 1/4 power times the Prandtl number. So, there is an unknown function of the Prandtl number here. Okay. Can we make this more definite? Okay. So, we can consider different cases. Okay. The first case is if we consider Grashof number large, Prandtl number small. Okay. So, this is the small Prandtl number limit. Okay. However, we require that Grashof number to the half times the Prandtl number has to be much larger than 1. Recall that this term appeared in the denominator multiplying the diffusion term in the energy equation. Okay. Grashof number to the half times Prandtl was in the denominator multiplying the energy equation. Okay. Let me just pick up that. So, here in the energy equation, this was the parameter. Okay. So, for convection dominated flows, this has to be a large number. Okay. So, we will consider first that limit. Okay. What does it mean Prandtl number small compared to 1? Okay. What it means is that the kinematic viscosity divided by the thermal diffusivity, Cp mu by K, that is small compared to 1. Okay. That means that the momentum diffusivity is much smaller than the thermal diffusivity. Okay. The momentum diffusivity is much smaller than the thermal diffusivity. Okay. That means that the momentum diffusion is much slower than thermal diffusion, and that means that momentum diffusion is neglected to a much thinner boundary layer in comparison to thermal diffusion. Okay. So, if I plot the energy, the temperature and the velocity fields close to the surface. Okay. If I plot the velocity and temperature fields close to the surface, okay, where z is the cross stream direction and x is the streamwise coordinate, okay, along the surface. Okay. So, if I plot the energy and the momentum equation, okay, okay. If I plot the temperature, for example, as a function of z, okay, it will decay from 1 at the surface. Okay. It will decay from 1 at the surface over some distance, okay, and that distance over which this thermal boundary layer decays, okay, over which this thermal boundary layer this temperature decays, is the thermal boundary layer thickness, okay, delta star, scaled by the characteristic length of the object. Okay. So, that is the distance over which the temperature decays. Okay. since momentum diffusion is much slower than thermal diffusion, you would expect the sharp gradient in the velocity field close to the surface due to momentum diffusion. The sharp gradient in the velocity field close to the surface due to momentum diffusion to be restricted to a thin region close to the surface, a momentum boundary layer thickness, okay, which I will call as delta V. Okay. This momentum boundary layer thickness I will call as delta V. Okay. So, this is the velocity Vx in the x direction, and this is the temperature T. Okay. Okay. So, outside of the momentum boundary layer region, momentum diffusion is small, and therefore, there is a balance between the inertial force density and the buoyancy force density. If you neglect diffusion altogether, you cannot satisfy the no slip condition. Therefore, there has to be a correction due to momentum diffusion within this thin momentum boundary layer close to the surface. Okay. Now, the thermal flux, the energy flux depends upon the thermal boundary layer thickness. Okay. The energy flux depends upon the thermal boundary layer thickness, and therefore, I have to rescale my equations by the thermal boundary layer thickness and get a balance between thermal diffusion and convection within the thermal boundary layer. Okay. Since the thermal boundary layer is much thicker than the momentum boundary layer, in the momentum equation, over a distance comparable to the thermal boundary layer, momentum diffusion will be small. Okay. Momentum diffusion will be comparable to inertial forces only within the momentum boundary layer, which is much thinner. Okay. So, therefore, I will rescale my z coordinate. Okay. I will call it as z double dagger, okay, is equal to z by the thermal boundary layer thickness times Lc. Okay. And therefore, the cross stream velocity will also be Vz divided by delta T times Lc, and I will determine the thermal boundary layer thickness from the condition that thermal diffusion and convection are comparable within the thermal boundary layer. Okay. I'll determine it from the condition that thermal convection and diffusion are comparable within the thermal boundary layer. Okay. So, my energy equation is Vx partial, so let me just write it in original form. So, Vx star is equal to Vx by Vc, okay, Vz sorry x star. Substitute this into the energy balance equation, okay, and I will get Vx, okay, partial t by partial x plus Vz partial t by partial z is equal to alpha infinity into, okay, partial square t by partial z square in dimensional form. Substitute the scalings. Okay, on the left side I will get Vc, okay, into by Lc, okay. Note that Vx by x and Vz by z are of the same magnitude, okay, in this case. Both of them go as Vc by Lc. Okay. On the right side I will have alpha infinity by delta t square Lc square. Okay. And I divide throughout by the prefactor of the convective term, and I will get Vx partial t by partial x plus Vz double dagger partial t by partial z. And I determine the thermal boundary layer thickness from the condition that this is 1, okay, for a balance between convection and diffusion in the limit of high Peckley number. Okay. And therefore, I get delta T is equal to alpha infinity by Vc Lc whole power half. Okay. I can also write this as alpha infinity by nu infinity into nu infinity by Vc Lc. Alpha infinity by nu infinity is 1 over the Prandtl number, okay, and nu by VCLC is 1 over the Reynolds number, which is 1 over the Grashof number to the half. This whole thing to the half power. Okay. So, this is equal to Prandtl number to the minus half, Grashof number to the minus 1 by 4. Okay. That is the thermal boundary layer thickness in this case. Okay. So, this is the expression for the thermal boundary layer thickness in this case. Okay. Now, this scaling for the thermal boundary layer thickness I could substitute into the momentum equation. Okay. I could substitute into the momentum equation. Okay. I will not go through the details here, but what you will get in the end is Vx, you can work it out for yourself using the same procedure that I have used over here. Vz double dagger partial Vx plus Prandtl number into okay. So, this is the momentum conservation equation in the streamwise direction. Recall that we are considering the limit of low Prandtl number, and therefore, within the thermal boundary layer the momentum diffusion is small compared to convection. Okay. You need to rescale the coordinate once again by Grashof number to the minus 1/4 power within a thin boundary layer close to the surface, so that momentum diffusion and convection become comparable, and then solve for the velocity field in this thin boundary layer region. Okay. Solve for the velocity field in order to satisfy the no slip condition. Okay. However, that does not really affect the flux from the surface. Okay. So, the flux Qz, okay, using the same arguments that I had used earlier, is equal to minus k partial t at z is equal to 0 by delta t. Now, the energy balance equation contains no parameters because this whole thing here is 1. Okay. The energy balance equation contains no parameters because in the thermal boundary layer this factor is equal to 1. In fact, we determined the thermal boundary layer from the condition that this factor is equal to 1. In the momentum boundary layer, if we neglect the viscous terms, because the Prandtl number is small, so if we neglect this viscous term because the Prandtl number is small, that also contains no parameters. Okay. Therefore, this partial t by partial z contains no parameters. Okay. I should have an LC here, my apologies. Okay. because Z double dagger is LC times delta T star. So, that also contains no parameters. Therefore, this contains no parameters. The average flux depends only upon geometry, okay, and it contains no parameters. So, the Nusselt number, which is equal to Q average by K into T naught minus T infinity by LC. Okay. This is equal to some constant for the limit of small Prandtl number times 1 over delta T star, okay, where that constant depends upon the average of this integral across over the entire geometry. This term contains no parameters, therefore, the integral will depend only upon geometry, okay, it does not depend upon the Prandtl number. Okay. So, therefore, this is equal to a constant for Prandtl number small compared to 1 times PR per minus half times the Grashof number per minus 1 by 4. Okay. So, this is the dependence of the Nusselt number on the Prandtl number and the Grashof number in the limit of low Prandtl number, momentum diffusion small compared to thermal diffusion. The effect of momentum diffusion restricted to a thin boundary layer, which is much smaller than the boundary layer for thermal diffusion. Therefore, the length scale for thermal diffusion goes as Grashof number per minus 1/4 times Prandtl number per minus half, so that there is a balance between convection and diffusion within the thermal boundary layer. Okay? And if there is a balance between convection and diffusion within the thermal boundary layer, the thermal boundary layer thickness has to go as PR per minus half times GR per minus 1/4. Okay? And the heat flux is proportional to the temperature gradient, which is the ratio of the temperature difference and the thermal boundary layer thickness. And therefore, the Nusselt number has to scale as PR per, I am sorry, it is not minus half, it is plus half. Okay? The Nusselt number has to scale as PR per plus half, okay, because it is proportional to 1 over the Prandtl number and the Grashof number. So, this is equal to PR per half times GR per 1/4. Okay? So, that is the correlation for the Nusselt number in the limit of in the limit of low Prandtl number, okay, when the thermal boundary layer thickness is much larger than the momentum boundary layer thickness. What happens in the opposite situation, where the momentum boundary layer thickness is much larger than the thermal boundary layer thickness, or in the limit of high Prandtl number? Okay. Okay. This is the case that I will consider next. I will continue this in the next lecture. Okay. I will see you then.